Yeah, so this entire week was allotted to clustering algorithms. So I will be covering two such algorithms which were covered in the course, k-means and hierarchical clustering method. So yeah, so I'll start. I hope my screen is visible.
Yes, perfect.
Yeah. Okay, so it will be, hopefully it will be a short lecture today. So the first thing is k-means clustering. So as all of you will know by now, clustering is an unsupervised algorithm. So k-means clustering, there are two major terms in that. One is k, the other is means. So k means you want to divide the data into k clusters, and therefore k needs to be known from before, and that is one of the major drawbacks of this particular clustering algorithm. There is a method where you can choose k, but the algorithm needs to know from before that needs to know the value of k before going about doing its job. That is one. The other is means, which effectively signifies the fact that we are considering clusters by virtue of their means, which is the average of all the points which are assigned to a particular cluster, and hence the name k-means clustering algorithm. And it is a hard clustering algorithm, which means that it does not assign probabilities to the points. I hope you saw that in some parts of the lecture notes, at least there were references to an algorithm called EM algorithm. So there is another popular clustering technique called Gaussian mixture models. So there you will so there it effectively gives a probability to a point. So let's say we have 3 or 4 clusters. So there every point will be given a probability that it has a probability of 0.5 of being in cluster 1, let's say 0.2 in cluster 2, and so on. But k-means is not like that. K-means gives a hard probability. So whenever a particular point is assigned to a particular cluster, that is a probability, the entire probability mass is given to that particular cluster. So that is a difference between a hard clustering algorithm and a soft clustering algorithm. So k-means is effectively a hard clustering algorithm. Okay, so how to go about it? The k-means is best.
Excuse me, sir.
Yeah.
So actually, I was asking, in soft clustering, the particular point belongs to both the cluster. That is the basic difference between hard and soft clustering.
A particular point there will be does not belong to both the cluster means in the sense of probability, that it has a probability of let's say 0.5 belonging to cluster 1, 0.2 belonging to cluster 2, 0.3 belonging to cluster 3. Okay, it does not mean that so that extra information comes to you. Here it will be like it has a probability of 1 belonging to cluster 1 and probability of 0 belonging to cluster 2 or 3. You got the difference?
Yes, sir.
Yeah, okay. So yeah, so k-means clustering is best shown by means of examples. So this is a toy example that I constructed. So let's say there are the colored points which you are seeing, they are basically the ground truth labels, and they are not given to you because this is an unsupervised algorithm. So they are on the x-axis and they will have certain values. So I will show you the values of these particular points later. So let's say the top 3 with the blue, green and the yellow, these are the 3 clusters that you have, and they are situated in this way on the x-axis. And the original data, the 3 clusters, they are visible to the eye but are not provided to the algorithm. So what the algorithm can start with is, it will start with all the points gray, which means none of the points are assigned to any of the clusters. So that is the first step. And then so basically the first step is, suppose we know k equal to 3. So that is the first point that you need to remember in k-means clustering, that you need to know the value of k before the algorithm can even start. So suppose we know k equal to 3. So what we do is we randomly select 3 points. So let's say randomly we select the first 3 points, and we assign, and we consider these 3 points to be the cluster centers. So these are all the cluster centers, and assign all other points based on the distance from the cluster centers. So if you consider the second diagram and the third diagram, you see that the first point is blue, and so that is already a cluster center, so we don't need to assign any color to this particular point. Yellow is again a cluster center, we don't need to assign any color to this particular point. Green is again a cluster center, the third point is we don't need to assign any cluster point. The fourth gray point, what we do is we compute the distance of this fourth point with the first, second and the third points, and whichever point is nearest to it, whichever cluster center is nearest to it, we assign it to that particular cluster. So the way these points, these last 4 points are situated, all of them will be given to the cluster green, and therefore at the end of the first stage you will see that there is only one blue cluster, 1 point in the blue cluster, 1 point in the yellow cluster, and 5 points in the green cluster. So I hope this is clear how this particular how the second diagram became the third diagram. So if it is not clear, then please ask me right away.
Yes, clear.
Correct. Okay. So so the next step that we need to do is, now the k is done, now we'll come to why it is called k means. So then what we'll do is we'll calculate the mean of all the clusters. So the blue cluster, of course, it has only 1 point, so the and now I'm introducing the coordinates because I have to do some calculations. So let's say the blue these points are situated on the x-axis and the values are 1, 2, 5, 6, 9, 10, 11. Some random values I've just chosen, so so these are just for calculations. So so the mean of the cluster, so the mean of the blue cluster will be 1 because there is only 1 point, and the yellow cluster will have a mean of 2, and the blue cluster and the green cluster will have 5 points, and if you divide it by 5, this is probably 11, 20, 30, 41, yeah, 41 by 5, which is 8.2. so the green cluster has a mean of 8.2. So that is the now we are going on to the second step onto the k-means clustering algorithm. So what you need to do is now you have calculated the means of these 3 clusters, and now again you will what you will do is you will go to each point and assign it to the mean which is closest. So now we have 3 means, correct? You have 1, 2 and 8.2 for the 3 clusters. So we will go to each point and you will see which mean is closest to that particular point and give it that particular color. For example, point 1 is obviously nearest to the blue cluster because that is the only one that is there. So 1 minus 1 is 0, 1 minus 1 whole square is 0. Suppose we are taking the Euclidean square of the Euclidean distance. So 1 minus 1 is 0 for the point 1. Point 2 is nearest to the yellow cluster because for the same reason as point 1. So point 2 will be assigned to the yellow cluster. Point 3, which is this third point, it has a value of 5. So it has, of course, let's see yeah. So the point 3 has a value of 5. So we have 3 candidate values of 1, 2 and 8.2. So you can see that the distance of 5 from 8.2 is more than the distance of 5 from 2, which is 3 square, and this is 3.2 square, and from 1 it is definitely farther. So point 3 distance from the yellow cluster is 3. Actually this is the root, I have taken the root, and distance from the green cluster is 3.2. The nearest cluster is yellow, and therefore this particular point, the third point, will turn to yellow in this particular stage. Okay, so and point 4, which is 6, point 4 which is a value of 6, that is again nearest to the green cluster because the value of 6, the difference between 6 and 8.2 is just 2.2, and 6 and 2 is 4. So are these 4 points clear? Why I mean, yeah, so are these 4 points clear? Point 1 to point 4.
So point number 5 is assigned to yellow, right?
Point number, not point number 3, which has a value of 5.
Point number 3. Then
yeah.
Point number 4, 5, 6 and 7 will be in the same cluster.
4, 5, this last 4 will now will remain green. This 5 will now turn yellow. Okay. So if you see here, this last 4 points are still green, these 2 points have turned yellow. Okay, so now the second iteration of this k-means clustering algorithm is done. So again you do the same thing, you calculate the means, you calculate the cluster centers. Means effectively means the cluster centers. So blue again does not change because there is only 1 point in blue. Yellow now changes from 2 to 3.5 because the average of 2 and 5 is 3.5. And green changes from 8.2 to 9. So if you sum this up, this will be 6 plus 9, 15 plus 21, 36 by 4 is 9. So green now changes to 9. So now if you start assigning points, so let's consider the first point. The average of blue is anyway 1, so it remains 1, it remains blue. The second point, which has a value of 2, the distance of the second point now has is 1 from the blue mean and 1.5 from the yellow mean. Correct? So because of that, this second point has now turned blue because it is closer to the blue cluster mean. Similarly, 5 remains as it is because 5 is much farther from 1 than 3.5. So and 6 now considers the point 6. So the fourth point, which has a value of 6, so it has a distance of 2.5 from yellow mean and it has a distance of 3 from the green mean, which is 9, and therefore 6 now turns yellow. And finally 9, 10, 11, if you compute in the same way, 9, 10, 11 will all be to the green category. So assign points to the cluster as before, and therefore we see and we know that this is the actual I mean in the first diagram itself I had shown that this is the actual clustering that was done, the actual cluster from which the data points had come. So assign points to the cluster as before, and we see that we have already got the correct result. However, the k-means algorithm will not stop at this because for k-means there is no ground truth. So the k-means algorithm will continue doing this unless it sees, but it has to stop at some point. So where will it stop? It will now compute the means of blue, yellow and green, and it will turn out to be 1.5, 5.5 and 10. Reassign the points again and calculate the mean. So what it will do is it will do this iteration again. It will calculate the blue mean, the yellow mean and the green mean, and it will reassign all the points again. And as soon as it tries to reassign all the points, it will and calculate the mean. After reassigning the points, it will see that the means have not changed. So once the means have not changed, then k-means clustering algorithm will stop, and it will say that these are the clusters that I have found, these are the means, and this is the cluster that I have found. Okay, is the stopping criterion of this clustering algorithm clear?
Yes, sir.
Okay, so now k-means, so I started with 3 random points here. So these are the 3 random points that I started with. So what about, but this is a random selection of points, and that too I am showing k equal to 3 out in a group of 7 points. So in practice you might have hundreds or thousands of points. So any random group, any random 3 points you can, so there can be many such random choices, and therefore k-means algorithm, usually when you give a k-means algorithm to through a package, it will run this algorithm multiple number of times. And generally k-means algorithm is never run once, it is run multiple number of times to improve on a particular metric. So we'll talk about that metric, what it looks at, but just to show in case that k-means might actually end up giving a wrong result. Let's say k-means algorithm was correct in the case that I have already shown, but what about if the initial 3 points selected were this 9, 10 and 11? So this might have been a very possible selection. I had selected the first 3 points, now I have selected the last 3 points. This is quite possible in a random world. So initial assignments will be as follows. If you follow these assignments, okay, where was I? Okay. Yeah. So if I take these 3 points as my initial points, then after the first iteration, these will be the these will be the clusters that will be formed. All the first 5 points will now become blue, the second last point will be yellow, the last one will be green. So if you sum them up now, then mean of blue will be 5.6, yellow will be 10 and green will be 11. Based on distances, reassignment will now work as follows. So what will happen is, you see this first point and you see this means, and you do the exact same thing as I had shown before. Just consider this 2 points 6 and 9, because these are the 2 points which might change. Other points anyway won't change, because the average is between 5 and 6 of blue, and yellow is 10, so it is much farther from 5 than 5.6. So anyway, 1 to 5 you don't have to check also. So the mean of blue is 5.6. So okay, the mean of blue is 5.6. So 6, the distance between 6 and the mean of blue is 0.4, and the distance of 6 from the yellow mean is 4, and therefore 6 remains blue. However, you see this 0.9, it is now much farther from the mean of blue than the mean of yellow, and therefore it will turn yellow in this case. So these 2 points become yellow, this point remains green, these first 4 points remain blue. Based on the distances, this reassignment will work as follows after the first step. Now if you do a k-means algorithm again on this particular assignment, you will see that these clusters won't change. These will be the final assignment by the k-means clustering algorithm. So k-means clustering algorithm ends up with a
money at disposal is key.
Hello? Okay. I thought I heard somebody speak. Anyway, so these are the final cluster assignments that will be done, and therefore this is an example of where if you start with random points, you might end up with very different results in k-means algorithm. And since it is an unsupervised algorithm, there is no way to know which algorithm is performing better than the other, which random seed is performing better than the other. Now, how to understand whether my k-means algorithm is performing at least well? That's the one thing, and also this gives us a handle about how to select the value of k. So with two different starting points, we have got two different results. This was the first one is basically the wrong assignment, the second one is basically the correct assignment. So what we do is we calculate the variance of each class. So variance is nothing but the value minus the mean of that particular class whole square. So for the first case, the blue class variance is 1 minus, so the blue class if you compute the mean of the blue class, it will be 1 plus 2, which is 3 plus 11, 14 by 4, which is 3.5. So the blue class variance will be 1 minus 3.5. You compute the variance of this particular blue class. I am talking about the top diagram now. It will be 17, and the yellow class variance will be 0.5. It is 9.5, and 9 minus 0.5 whole square plus 10 minus 0.5 whole square will be 0.5. Okay, so in this way, what will be the green class variance? Can somebody say? For the top diagram?
0.
Correct. It will be 0 because the mean, there is only 1 point, so there will be no variance for the green class, and therefore the total variance on the first diagram is 17 plus 0.5 plus 0, which is 17.5. That is a particular value that you have got. In the second case, for blue and yellow, it will be 0.5 because it is the same as the yellow in the first case. So I have not shown the shown the calculations. So blue and yellow will be 0.5, and for green it will be 2. So the average of green is 10 in the second diagram, and 10 minus 9 whole square plus 11 minus 10 whole square is 2, and therefore the total variance in the second case, in the second diagram, is 3. So total is 3 versus 17.5, and we say that whenever there is a interclass variance, or rather the intra-class variance, the variance within a particular class, if you add them up for all the classes and you find that one particular assignment is lower than the other, then the lower ones is the assignment that you will consider, because that means, because what does this variance effectively show? It shows that, you see, the blue class variance is 17 in the top case, and that is actually an indicator of the fact that the maximum values or the minimum values in this particular cluster are much farther than the mean, and therefore this cluster has taken up is spread out over a larger space on the x-axis, and I don't want that. I want the points which are close together to be in the same cluster, and therefore we take the assignment which has a total variance across the clusters lower. So that is how we understand whether between two assignments which one is better. Okay. Now this also gives us a handle about how to select the value of k. So how to select the value of k if it is not known from before? So that is another question that is always there in k-means clustering algorithm. So there is a empirical way. This is not a mathematical deep mathematical result. This is an empirical result, and this can be shown by this particular example. I have taken the same example, and let's say k equal to 1. So k equal to 1 means all are belonging to the same cluster. So that is 1. And let's say now I have increased k to 2. The point here is I don't know the value of k beforehand. So I am trying to select the value of k. So another value is k equal to 2. So these are the two clusters. These are the cluster assignments that I have got for k equal to 2. For k equal to 3, I have got the correct thing, as I know that these are the clusters. And k equal to 4, the first 2 points are in one cluster. The next 2 points are in the second cluster. The fifth and the sixth point are in another cluster. The last point is in a separate cluster on its own. So this is k equal to 4. And now what you do is you select the you calculate the variance for all these clustered assignments. So if you see for k equal to 1, if you compute the variance of this, it will be 91.43. For k equal to 2, it will be 19. For k equal to 3, it will be 3. And for k equal to 4, it will be 1.5. Okay, what will be this value if I set k equal to 7?
Will further decrease.
I heard an answer, but somebody also said something else. Do I need to
decrease further? It may decrease further.
No, it will decrease. Can you say the value to which it will come to?
0.
Okay, it will be 0. Why?
Because the points itself, there will be no variance. The variance will be 0 in each case.
Correct. So so that's a good answer. So so if you consider there are 7 points here, and if I say k equal to 7, that means each of the points will be assigned to one cluster, and therefore there will be no variance for any of the clusters, and the total value will be 0.
Yeah. Yes.
So now that is an so of course, as I said to you, that that you will take an assignment which is which has the lowest variance. So in that case, in all k-means clustering algorithm, you should always select k to be the value which is equal to the number of points in the cluster, which are equal to the number of points in the data set. But first of all, that is impractical, because you might have lakhs and millions of points, millions, trillions points in your data set. That's the first thing, and k-means, and that's the first thing. And second is, you are doing the clustering algorithm in order to find out similarities between points. If you just go on and say that you have given me 100 points, and I am saying you that all the 100 points are different from each other, then that doesn't make any sense to work on the k-means to work on the clustering algorithm in the first place. So you cannot go on increasing k equal to the value of k and to reduce the variance. So you need to find out a particular way where the variance reduces suddenly. So that is known as the elbow method. So it's like if you put down your elbow, so the point where your elbow hinges, the hinge of your elbow is the value of k that you will select. For example, you see that I have plotted these values which I had calculated in the last slide. So for k equal to 1, it is 91.43. For k equal to 2, it comes down to 19. For k equal to 3, it comes down to 3, and k equal to 4, it comes down to 1.5. So, and it will go down to 0 as I increase it to 5, 6 and 7. So I have not shown those. Here if you see, the elbow effect is seen at 2 as well as in 3. So the k-means clustering algorithm, since you don't know the the number of clusters, you might as well choose 2 and you might as well choose 3, because it doesn't matter in this case. So, so I hope this is clear. This is also known as the elbow method. Sometimes what you see a plot of this is you choose the reduction in variance on the y-axis, and then this graph becomes a mirror image. So effectively it becomes so I hope you understand that this will become a mirror image if I change the y-axis from variation to reduction in variation. So it will go on increasing, finally it will taper down like this, and but just looking at this graph, you can think that whenever the variation reduces suddenly, like on a hinge, that is the value of k that you should select for your clustering algorithm. Okay, so yeah, I hope this is clear. Yeah, so that is about k-means clustering algorithm. If you have any questions, you can ask on the k-means clustering algorithm. Okay, no questions. That means either everybody has understood or nobody has understood.
We are understood.
We understood.
Okay,
Yeah.
okay, then great. Okay, then I'll move on to the next part, which is hierarchical clustering algorithm. And there are two approaches to it. One is the divisive approach, which is a top-down approach, not the top-down, bottom-up. I've forgotten. So divisive, one is the divisive approach, other is the agglomerative approach. So this is the top-down approach effectively. So it is called AHC, and and it creates a structure which are known as dendrograms. And there is another approach which is just the reverse of this, and AHC is the more widely used clustering algorithm. So I'll talk about that. So this particular example I've taken from the internet. I've given the link of this also. So for n data points, there will be n clusters. So let's say that these are some 6 data points, and there are some, so we don't know how many clusters are there. So initially we start with saying that all of the data points are on their own, all of them are separate clusters. So now what we'll do is we'll take the closest data point. So we'll compute the distances between all the data points with one another. Now there can be different metrics for distance, like there can be Manhattan distance, there can be a similarity function that you could compute, there could be a simple Euclidean distance also. So let's say I will take a distance of you take a distance of your choice, and you find out the distance between all the points with one another. You compute all pairwise distances, and you take the smallest distance between any two pair of points and you merge them into a single cluster. So now after merging, so if you see here the red one with the red circle which has come, because of this red circle now there will be one cluster and the remaining clusters are as it is. So there will be n minus 1 clusters. So initially there were 6 clusters, now there are 5 clusters. Okay, so now we'll continue doing this. So the next step would be, again we would we would compute the clusters. And now how to compute the distance of between two clusters is something that I'll come to later. There are several techniques of doing it. But one technique is you just think that somebody has come and told you how to find out the distance between different clusters. So you compute that again for all the clusters, and then you find that these two blue points are the one which are closest to one another, and therefore you also make them into a cluster. Now after you do the leftmost diagram, then you come to the middle, the second diagram. Now again you do the same thing and you continue doing this until you get a big, every point becomes in a single cluster. So this is the final clustering that you have done. So you started from here where none of the points were basically clustered, and finally you have gone to a point where all of them have become to one big cluster. So what is the use of this? Now we create the Dendogram. So the Dendogram will tell us how so we actually followed a particular procedure but finally we ended up with this big cluster. So the dendrogram is something which records the procedure that we went through in order to compute the final big cluster. So if you see, the first thing that happened was these 2 points were clustered in the first case. So P2 and P3, I don't know whether it is visible or not, but P2 and P3 are the points which were clustered first, these 2 points. So you see P2 and P3 are clustered here, and the Euclidean distance, if you see the Euclidean distance, which is the length of this bar, this Euclidean distance is the smallest among all other points. I hope you can understand this. So P2 and P3 are clustered first, and they form a particular one single cluster at this. They form a single cluster after P2
Sir?
and yeah.
Actually, sir, I have not understood the final cluster, how it has formed, because there is no point remain.
Yeah, so final cluster will be like you will find this particular, you will compute the distance between these two clusters in some way, and you will just cluster all of them into a single point. That's it.
Euclidean distance, na? So
Euclidean distance. So there are different ways to compute the distance between these two clusters. So
yes, there is a centroid and all.
there are three. I will talk about
Average.
3-4 different ways. So you compute the distance between these two clusters and just make them into one big cluster, and that you so I'll talk about this while creating the dendrogram. So just stay with me for now. So let's say so the first thing which happened was you clustered P2 and P3. So you clustered P2 and P3 together. So that is the meaning of this particular branch, and the height of this
based on distance or based on similarity.
That is up to you. That is again your choice. Here I think the example is based on Euclidean distance. So you can also take similarity here, that doesn't matter, or inverse of similarity in some sense. Okay. Yeah, so P2 and P3 is so P2 and P3 are closest to each other in this particular diagram, and therefore we combine them into a single branch. We combine them by this particular branch, and the height of this branch will be equal to the Euclidean distance between P2 and P3. So after you have clustered P2 and P3, now P2 and P3 becomes one particular cluster. After P2 and P3 has become one particular cluster, the next step that you did was you did P6 and P5. You clustered P6 and P5. If you remember, P6 and P5 were clustered next. So that also gets recorded in the dendrogram, that P5 and P6 is the P5 and P6 are clustered next, and the Euclidean distance of between P5 and P6 is more than that of between P2 and P3, but lower than all the others. So P5 and P6 are clustered next. After P5 and P6 are clustered, then then here it is, I mean, by design maybe it is shown. Okay, then this particular point is clustered. So if this particular point is clustered, I mean, I don't find the difference between these two bars. There should be some difference anyway. So P5 and so P4 and P5 and P6 will then become the cluster according to this diagram. So if P4, P5 and P6 become a cluster, that means after that this particular cluster will come in, following which P1, P2, P3 will come in, and after P1, P2, P3 and P4, P5, P6 have been given two clusters, which is this particular diagram. Then what you just need to do is you just need to compute the distance between these two clusters. You just need to find out the distance between these two clusters. Use that value here, put the value here in the dendrogram, and just join this by this particular bar. Somebody had asked that how the final cluster was formed. Is this clear now?
Soumya,
Yeah.
then we have clustered P2 and P3. Okay.
Yeah.
Then we are going to cluster P1 and the combination of P2 and P3.
Yes.
So again, the Euclidean distance is calculated between P1 and that
Cluster.
combination.
Yes. Yes.
Can you say what the blue lines, the blue horizontal
Yes,
lines
I'll,
are in the
I'll,
graph?
yeah, I'll talk about that. I'll talk about that now. I mean, is the how the diagram is created, is that clear?
Yes.
Okay.
Yes.
So now let's talk about
And
the, yeah,
one more doubt, Soumya.
yeah,
You
yeah.
you said it is a top-down approach, but I see this
It's
is
a
a
bottom
bottom-up
up approach,
approach.
but I don't know. I might have messed up the names also. You just remember that this is known as agglomerative hierarchical clustering. There is another thing which is known as divisive approach. So this actually should be bottom up approach. I might have made a mistake there. Okay. Yeah. So the other approach
So,
is, yeah.
so
Yeah.
actually, I was asking if there is a minimum distance between these two clusters, then it should be colored as green or red. Purple, how means that will be from another clusters.
Which one I see? The first thing is here, if you consider these two, if you consider these points, okay, let's say you consider you have these points. So you can, I hope you can understand that these 3 points look, I mean, if you are supposed to make it into 2 clusters, then maybe these 3 points and these 3 points will become the clusters. Is that I mean, intuitive to you?
Yes.
Correct. So if these are intuitives, then let's say these are all the blue points and these are all the green points. The colors don't matter, because finally you won't be able to color anyway. You will finally look at the different classes. So coloring is just for giving you an idea about how the clusters are formed. So basically here all the blue points are here, and all the yellow points are here, and finally you have colored all of them blue, which just means that all of them belong to the same cluster. Okay, and so similarly here what you are seeing is all of this, all the points which are within this red dotted curve, they are in the same cluster. All the points which are within this green dotted curve are in one cluster. All of them which are in the big blue ellipse is or some rotated ellipse is in one cluster. So that is all that is meant by this particular diagram.
Got it, sir.
Okay.
That means this purple color just showing the symbol of similarity, not
Similarity.
forming of another
Exactly,
cluster.
exactly. It's just showing a similarity that all of the points which are within this ellipse belong to the same cluster. That's it.
Soumya, how it is going to treat the outliers now?
It will get affected by the outliers. Of course, it will get affected by the outliers.
Let's assume there are 2 outliers, and then how you are going to cluster it?
No, finally it will, finally hierarchical clustering will end up putting all of them into a single cluster. Only then it will end, and it will create this dendrogram. Then it is up to you how to use this dendrogram to select how many number of clusters you want.
I think the outliers needs to be removed first.
That is up to you. I mean, if you, for example, yeah, so let's come to this blue lines, and then maybe we'll understand. Okay, so the blue lines means if you cut the dendrogram at this particular level, how many clusters you get. So I don't know why 2 clusters have been written here, but 2 clusters should ideally be written here. Like if you cut the dendrogram at this level, which is, let's say, 21, this particular level, you are getting 2 clusters, which means that P1, P2, P3 belong to one cluster, and P4, P5, P6 belong to the other cluster. That is the meaning of this blue curve. Similarly, if you break the dendrogram at this particular level, then what you get is, then how many clusters do you get?
4 clusters.
You get 4 clusters, where P1 is in one cluster, P2, P3 is in another cluster, P4 is in another cluster, P5, P6 are in another cluster. So you see that the dendrogram has cleverly recorded all the iterations of this. Okay, sorry, my computer has become very slow. Yeah, so the dendrogram has recorded all these steps one by one. You see, at the final stage, there is only one cluster. Next, you had 2 clusters. Next, you had 3 clusters. Okay.
Always starts with 2.
It will always start with like that. It will always look at the nearest 2 points, make them into a single cluster. It will always go on like this. Okay. in this particular approach. Okay, so now coming to the other question that is on the top of, that actually should be on the top of everybody's mind, is how to compute the distance between two clusters. So the first question is how to compute the distance. What is your distance metric? So the distance metric can be Euclidean distance, or it can be Manhattan distance. It can be some similarity of some inverse of the similarity function between 2 points, and so on. So you can have different sorts of distances. So the Euclidean distances are widely used. Manhattan distances are also used. Note one thing, that depending on the distance, your clustering algorithm might change drastically. There might be a drastic difference between your clustering algorithms depending on your distance metric. So you have to choose your distance metric properly. So so Euclidean distance is one. So I think most of the examples show Euclidean distances anyway. So distance between clusters. So after you have chosen the distance metric, how do you choose the distance between clusters? Because clusters will have multiple points. So one point is single linkage. So single linkage is the distance between two closest points of clusters. So which means that this is also known as the mean of the two clusters. So you have these you have these 6 points in the blue cluster and 5 points in the in this particular yellow cluster, and you take you compute the distance of all of these points with all pairs of points between these two clusters, and you take the minimum distance of those, and that you say to be the distance between two clusters. Okay, so that is known as single linkage. And of course you might have guessed, since there is something called single linkage, there is another thing called complete linkage, which is the distance between the two farthest points of the clusters. So you just take again you take the pairwise distances, and you take the maximum of all those pairwise distances, and that you assign to be the distance between two clusters. Another is centroid linkage. You compute the centroid of the two clusters, and you take the difference, and you take the distance between the centroids of the clusters. That is another way of computing the distance between two clusters. And okay, so now we have computed the distance between the clusters. So let's say so how to use the Dendogram to determine the number of clusters. That is the final question that is there in hierarchical clustering. So to determine the number of clusters, you have to check for the Euclidean distances. Okay, this E should be capital. Okay, check for the Euclidean distances between the clusters when deciding on the location to cut the Dendogram. As I told you that the position where you cut the Dendogram depends, that decides the number of clusters that you will have in your particular algorithm. So yeah. Okay, so let's say I have 4 candidate points where I 4 candidate points or 4 candidate rectangles where I want to cut the particular Dendogram, this particular Dendogram. Okay, so so if I cut the Dendogram somewhere within this rectangle, which is shown by this diagram, which is shown by this arrow 1, this means that I am cutting at this level, and the Euclidean distance between this between the right blue cluster and the first of all, somebody can you say how many number of clusters will we end up with if we cut anywhere in the rectangle 1?
2.
Yes. So if we are cutting anywhere in the rectangle 1, we'll end up with 2 clusters, and the Euclidean distance of these 2 clusters is given by the height or the length of this rectangle. Is this clear?
Clear.
Okay, if this is clear, then the other points will be pretty simple. If
So please repeat.
yeah, so you and I told you that on the y-axis I have plotted the Euclidean distance. So the length of this rectangle is actually an Euclidean distance between the 2 clusters that you will get if you cut anywhere in the rectangle 1. Is it clear now?
Yes.
Yes. So Now,
which distance is to be considered single linkage or
no,
complete linkage
so
or centroid?
that is up to you. Somebody has done that already for you and given you this dendrogram. See, while creating this dendrogram itself, you will decide what linkage you will use.
What is the difference between single linkage and complete linkage, Somya?
Here I told you here, right? Single linkage is the distance
Please,
between.
please have a quick recap.
Yeah. Single linkage is the distance between the two closest points, and complete linkage is the opposite of that, distance between the two farthest points.
Got it.
Okay, so 1, 2, 3 and 4. So should, okay, somebody can you say intuitively that whether we should cut it at 1? Somewhere
Distance will be more, no?
Distance is less, right?
distance is less, so should we cut it at 1? Hello?
Distance is less, that's why we are not cutting.
Distance is less, that's why we are not cutting, is it? Okay. Hello?
Yes.
Yeah. Why?
Yeah.
Why?
Because single linkage means
No, don't think about single linkage now. There is some linkage which have been done and the dendrogram is drawn. Why do I want to? You are correct. Your answer is correct that I don't want to cut it in the first block, in the first rectangle. My question is why?
The distance between any two clusters should be as large as possible.
Exactly. That is a good answer. So, so that is the reason why we don't cut in the first rectangle, because if we cut in the first rectangle, then the Euclidean distance between the two resulting clusters will be very low, and in clustering all you want is your clusters to be far apart from each other. So in no sense should you cut it at the cluster level 1. Similarly, I hope you understand that you shouldn't cut it at the cluster level 3 also, because the Euclidean distances at this particular level also is much is less. Now you see, like in K-means algorithm, I showed you a way where there were two. So I mean, even for k equal to 2, the elbow method, you very well would have ended with k equal to 2 by the elbow method. So here also you have been given two options, like 2 and 4. Exactly they may not match. So but visually it seems like 2 and 4, both of them are equally good. So but when 2 and 4 are equally good, it's always a better idea to go with the one which gives you a larger number of clusters. So when you are getting a larger number of clusters, you will probably get a better result, but these are all heuristics, so it depends on your final problem. So finally we can choose either 2 or 4, but selecting at 2 will give you, if you cut it at the second in this particular rectangle, you will get 3 clusters, green, blue and red. If you cut it at the fourth rectangle, you will get 1, 2, 3, 4 and 5. You will get 5 clusters if you cut it at the fourth level. So is this clear now, how to use the dendrogram to select the number of clusters?
Sir, can you show the Euclidean distance through your cursor between
Euclidean distance is the y-axis. So so Euclidean distances are plotted on the y-axis. So Euclidean distance between any 2 points, I mean between any 2 points or any 2 clusters, whatever the Euclidean distance is, you will plot it on this particular, I mean for example this will be the Euclidean distance between the red and the blue cluster. Okay.
And
yeah,
you know, out the distance between 2 points, we are considering Euclidean distance.
Yeah.
To find the distance between 2 clusters, we are taking this linkage approach.
Yeah. Yeah.
Linkage, complete linkage or the centroid linkage.
Yeah.
What approach between a point and a cluster?
It's the same thing, right? So basically your cluster, see the first point is in hierarchical clustering is for n data points there will be n minus 1 cluster, for n data points there will be n clusters. So all of your a point in itself is a cluster.
Right.
So there I mean if a cluster has only 1 point, their single linkage, complete linkage, centroid linkage, everything will become the same.
No, you will have, while doing this cluster mapping, you will come across a scenario where you will have a point and you
Yeah,
want to
let's
get
say,
that.
correct. So let's say I am looking at this particular case,
Yes.
and I'm trying to move from the second diagram to the third diagram.
Right.
Okay, so what you will do is you will take this point, and let's say you are doing centroid linkage. You are, for some reason you have chosen centroid linkage. So what you will do is you will take this point, you will compute the centroids of these two clusters and compute the distance from this point and the two centroids.
That means to compute the distance between a point and a cluster,
Yeah.
you can take any one of the approach, the complete link, single link.
One thing is, once you start to use a particular approach, you will have to keep on using it in that particular algorithm.
Okay. Right.
Okay. So you just think of this point as a cluster itself. So the centroid of this point is again itself, right? So basically this cluster, I mean, it is generalizable to all such definitions in that sense. Even if you have one point, your centroid remains that point itself. And if you want to calculate the distance between two clusters by means of centroid, then you just compute the value between centroids of different clusters, which if you have a single point is just the difference, is just the distance between that point and the centroid of each cluster. I hope I am clear now. Yeah. Okay, so that is it about hierarchical clustering. This is also, I hope this was simple only. Now this is a question, I mean, I found it from the last year's assignment. So these are very badly drawn diagrams. I'm sorry for that, but it is the way, that is the way it is. So the question here is, which of these, I have shown two dendrograms. So which of this is the mean linkage out of these two dendrograms and out of these two, I mean these two clustering algorithms, let's say. Which one of them has used the mean linkage, the other one has used something else. We don't know what that is, but which one has used the mean linkage, where these are the 6 points that you have, the black points, and the clusters are shown here, like 3 6 is the first cluster that you have got, 2 5 is the next cluster that you have got, then you have combined 2 5 and 3 6 as the third cluster, then you have combined 4 in the fourth cluster, finally you have got 1 in the fifth cluster. And similarly you can consider this, the bottom diagram also. So which one, okay, so can somebody guess, I mean what should we see, like which step should we look at to find out which one is the mean linkage? I don't want the answer, but if you are given, if you are given this question, what is the step that you should look at?
You should look at the minimum value between 2 points.
Between 2 points, okay. So so we are talking about mean linkage, remember. So mean linkage will come into play only when there are some clusters formed. Am I correct?
Right.
So in that case, if we are talking about the situation when some clusters are formed, which is the step that, I mean, which is the step that we should not look at, first of all? Which is the first step in the dendogram which we should not look at, because that will not give us mean linkage.
So we have to find which linkage we have used in this question.
Yes.
So sir, I think second is a single linkage and first one is complete linkage that we have used.
No, I'm okay. Okay, continue. Why is second one the single linkage?
Because sir, as in the lecture, we have learned that in single linkage we use long and thin circle, and while in complete linkage there should be a tight spherical shape. So I think second one is single and first one is complete linkage.
I did not use those words. So don't think about those things. Don't look at the diagram also. Just single linkage means that when you are computing the distance between two clusters, you are taking the minimum distance of the points. I mean the shortest distance among all such points. Okay.
Closest points.
Closest points. So in this case, Okay, I will give you a hint. Just okay. Let me ask you one question. When we are forming cluster 1, is there any reason for cluster 1 to give us information about whether there is single linkage, complete linkage, anything?
No, not required.
Why? Why?
Because there are only 2 points, na, so there is no nearest point.
Correct.
Both
So
are
when we are creating the first cluster, we don't have any information, we don't need to have any information about this single linkage, complete linkage, whatever, because all the points are there on themselves. I mean, they will now be clustered. So how the first cluster is formed doesn't matter to us. Now let's see how the second cluster is formed. So in the top diagram, you see the second cluster is formed, means 2 and 5 are now clustered. So what is the distance between 2 and 3, the points 2 and 3? Because of course, if you now consider all the points, so okay, how can I say this? Now see, 3 and 6 are already into a single cluster. So there are 1, 2, 4 and 5. There are 4 points outside which you need to assign to, which you need to understand what cluster you will now, which 2 points you will now merge. So one thing which you will do is you will compute the distance between all such points 1, 2, 4, 5 with 3, 6 cluster. This is a cluster now at the second stage. So when you do that, what is the so if you had gone by min linkage, then what will you see? Suppose you are looking at the distance between the point 2 and the cluster which you have formed in cluster 1. Which is the distance that you should look at when you are trying to compute the distance between 2 and this cluster?
between 2 and 3, no?
Between 2 and 3. So in this distance matrix which is given, the between 2 and 3, the distance is 0.1483. I hope it is visible. I mean
Yes, you highlighted it.
yeah. So it is 1.1483, and if you see the distance between 2 and 5, it is 0.1388. Okay. So between 1388 and 1483, you have got 2 and 5, because you have chosen the lowest of these two distances. And therefore now we have got, and if you see all the other distances, 0.1388 will turn out to be the lowest distance, and therefore 5 and 2 are the second cluster. So now we have got no difference between the two diagrams. Here also the first cluster was 3 and 6, the second cluster was 2 and 5. So 3 is however different between these two. So that is the question that I was asking. You have to look at these two diagrams and immediately you have to find out, and if you are to find out the distance, or rather the difference between these two algorithms, the first point you should look at is where they actually differ. Am I correct?
Yes.
So 1, 2 and of course 1, 2, both of them have been formed in similar ways, and therefore 3 is the one where we should look at. So 3 in the top diagram is given by 2, 5. They have actually merged 2, 5 and 3, 6 into one big cluster. Here they have done something else. They have merged 3, 6 and 4. So now from here, can you say which one is the mean cluster, linkage, and which, or rather the single linkage, and which one is the complete, or which one is not single linkage?
First one is not single linkage.
First one is
not single linkage.
Why?
Second one is the single linkage.
Why?
Because there is a least distance between 3 and 6, cluster 1 to 4. Distance is minimum between cluster 1 to 4 in second diagram.
There is a minimum distance between cluster 1 and 4. Yeah, why? What is the distance between the point 4 and 3 and this cluster 1 if you are going by minimum linkage?
Excuse me?
What is the distance between this point 4 and this cluster 1 if you are going by single linkage?
Okay.
You have to look at this particular row of this
A
distance
table.
matrix. So what is the distance?
It is between P4.
15, 13, no? Between
Point
P4 and P3.
1513.
P4 and P3.
Correct, it is 0.1513 because your candidates are 0.1513 and 0.2216, and since you are going by min linkage you will take 0.1513. Okay,
It is a minimum.
so it is 0.1513. Now what is the distance between the cluster 2 and cluster 1? What is the distance between cluster 2 and cluster 1?
0.1483. 1483.
Why?
P2 and P3. P2 and P3 we are going to compare.
Yes, so which one is the minimum linkage between these two?
P2 and P3.
Yeah, so between these two dendrograms, which one is computed by the minimum linkage? That is the final question. Now, you have answered everything. So, what should be the
point 2 and 3, no?
Point 2 and 3 is the minimum linkage. So, if point 2 and 3 is the minimum, see, the other option is, of course, 1 you leave, 1 you don't need to worry about. You need to find out the distance between 3, 6 and 4 and 3, 6 and this cluster. That is the only difference between these two diagrams, correct? In the bottom diagram, 3, 6 or the cluster 1 was merged with the point 4. In the top diagram, cluster 1 was merged with cluster 2. Am I correct? So if you had gone by single linkage, then by the calculations that you showed, then P2 and P3 has a distance of 0.1483 and P4 and cluster 1 has a distance of 0.1513. So you should obviously select cluster 2 as your third cluster. Is this clear?
Okay.
Is this clear to everybody?
Yes.
Means the single linkage between any two clusters, if it is minimum, then those two clusters should be combined together to make another cluster.
Correct, exactly. Right. So here you see that in the second diagram anyway, in the bottom diagram anyway, if you had single linkage, then you would never cluster 3, 6 with 4. You will always cluster 3, 6 with cluster, you will always cluster 1 and 2 to form cluster 3. So therefore the top one is the single linkage 1 dendrogram. I hope this example is clear.
Got it.
Yes.
Okay, so that is it. So I gave you a brief idea about k-means and hierarchical clustering algorithm. So if you don't have any more questions, then I'll close the session, and it was good teaching you all. So
for this last example, so which one is better in the dendrograms?
Which one is better is a difficult question to answer. Basically,
in the assignment question, I have given 4 ABCD. So the question is, which of the following clustering representations and dendrograms depicted the use of minimum or single link proximity functions in hierarchical clustering?
Yes.
So 4 diagrams are given.
I think I copied the same question maybe. I don't know.
CD are given, CD are not given.
CD I have not given because it did not fit into the slide. So if you go by the algorithm which which we just worked on together, then you will understand that it is quite simple. You first step is to find out where where all the diagrams differ. Once they differ, then you will have to find out when only one of them will have a single. So if you go by single linkage, only one of them will probably come out correctly. Okay, so that is the way you need to understand.
Right, thank you.
Okay. Okay, so
previous slide, please go to the previous slides.
Here.
We have to cut this dendrogram at level 4, no?
Level 4, yes.
Yes, to get the maximum Euclidean distance, right?
Yes, yes.
Okay, okay, thank you.
Yeah.
But sir, according to y-axis, the maximum distance is present at 1. So
No, maximum distance is not present at 1, right? See,
400
no. See, the way you are computing this is, the way you should interpret this is, when you are cutting at 1, you understand that there will be two clusters, right? This the left blue and the right blue.
Yes.
And the distance between these two blue clusters will be given by the length of this rectangle. Height of this rectangle.
Oh.
Yes,
okay.
Consider the height, not length.
Height of this rectangle. So if you are looking at the height of this rectangle, then the height of this rectangle you see is the lowest in 1 and it is maximum in 4. That is why you cut it at 4. Because what do you physically or what do you intuitively mean by the height of this rectangle? You mean that is the Euclidean distance between the two clusters that I am getting, and you always want clusters which are vastly different from each other. If you have the Euclidean distance to be very low, that means your two clusters are anyway very close to one another. There is no point in getting those two clusters. Okay.
Got it, sir. Perfectly. Thank you.
Excuse me.
Yeah.
Will you please explain it once?
This particular diagram, is it?
Yeah, hierarchical clustering diagram.
Yeah, so once you build up this dendogram, so what you need to do is, this dendogram is, this is exactly built like I showed here. Like I went through this example how this small dendogram was built. So this is a small one. Let's say I have a big dendogram like this. So all these vertical lines, they are all these vertical lines are the Euclidean distances between the two clusters that I am combining at this particular level. Okay. So now I want to find out how many clusters I will end up with, how many clusters will give me a proper representation of my data. So there are the first option is of course to cut at the top. So there you will get two clusters. If you cut anywhere along the length of the rectangle 1, you will get two clusters. It's correct. I mean, this one is this much is understandable, right?
Okay.
Now similarly, if you cut anywhere in this rectangle 2, you will get three clusters. You will get the green ones, you will get the red ones, and you will get the blue ones. You will get three clusters. Similarly, if you cut at the third rectangle, you will get 4 clusters, and if you cut at the fourth rectangle, you will get 5 clusters. So once you have got these clusters, how to decide how many clusters, where you will cut the dendogram? So depending on so when you cut the dendogram, that means that probably when you cut in this rectangle 1, then the difference or the Euclidean distance between the two clusters that you will get is equal to the height of this particular rectangle. And since this height is very low, the two clusters that you get are mostly similar to each other, and that defeats the purpose of clustering algorithm altogether, because your two clusters are very similar. There is no point in clustering them. So then you come down to 2. 2 is obviously much better than 1, but of this 1, 2, 3 and 4, of course you can go down further, but 4 will be the highest. So once you go down to 4, you see that the Euclidean distance of this 4 or the height of this particular rectangle in 4 is the highest, and therefore these 5 clusters is the one that you should choose. So your algorithm should aim to divide your data into 5 clusters. That is what is meant by this diagram. Yeah, I hope it is clear now.
Yes, thank you.
Thank you.
Okay, so if there are no more questions, I will close the session.
Actually, hello sir.
Yeah.
So actually this is the last lecture and I don't want any question in my mind. So please can you repeat the last thing, that was the simple linkage and complete linkage?
Okay, yeah, simple linkage is simple, yeah, single linkage. Single linkage is when you have two clusters.
No sir, it's not.
Hello?
So we are discussing about, yes.
Hello? Yeah.
So the last slide.
Oh, here. Okay,
yes,
okay.
One. Yeah.
Okay, so you got that we need not look at how the clusters. Okay, can all of you mute, please? I mean, except the person who is asking the
Ma'am,
question.
please mute.
Yeah. Okay. Yeah. So. Yeah, so you understood the first thing was we need not look at how clusters 1 and 2 were formed, because both of them are same in the two diagrams. That is clear, right?
Yes.
Okay, so the first point where these two diagrams differ from one another is 3, how the cluster 3 was formed. So in cluster 3, in the top diagram, cluster 1 and cluster 2 were merged, and in the bottom diagram 3 6 and the point 4 was merged. So let's see the mean linkage distance between point 4 and the cluster 1. So that will be the minimum of the distance between 4 and 3 and 6. So the distance between P4 and P3 is 0.1513, and the distance between 0.4 and 0.6 is 0.2216. So P4 and so P4 and so the distance between the 0.4 and 36 and the cluster 1 is 0.1513, the minimum of 0.1513 and 0.2216. Therefore that comes out to be 0.1513. But if you look at the distance between cluster 2 and cluster 1, then visually you can see that 2 and 3 are the closest points. So you can look at point 2 and point 3, it is 0.1483, which is lower than 0.1513. So if you are going by mean linkage, you will never choose 0.1513 over 0.1483, and therefore you will never do this particular clustering. Is this clear?
Yes.
So that is why the top one is the cluster that is the clustering algorithm which follows the single linkage or mean linkage distance metric.
So actually I was talking about the shape. If the shape is tighter, then it will be called as complete linkage, as we have learned in the lecture. So
you don't I mean, see, these are all representative diagrams, so you should not look at the shape and try to find out what is happening. Because all the distances are given here, so it's better to look at the single linkage. Or see, one more thing, I mean, if you are trying to understand from that point of view, that what is single linkage and what is complete linkage, I would suggest the better way is to look at the dendrograms. I hope you remember that dendrograms will be tall and so on in single linkage, and in complete linkage it will not be tall, it will be something like that was written, right? So you see this dendrogram is taller than this particular, I mean it's thinner, taller and so on. So this dendrogram it looks thinner than this particular dendrogram, and so this is not the correct way to understand which is a complete linkage, which is a single linkage. The best way to understand is to work out in the proper way. Okay, so I would always suggest that.
The scale is changed, in that case the height will change.
So it should not be looked at in that way. So it cannot be measured by that. So I would always advise you to look at how the things are calculated. I mean, these are pretty simple things. It's just that you have to keep in mind what is happening. Step by step, if you go, it will work out.
So Euclidean distance is the only measure, sir?
Here the distance is already given to you. You don't know what distance is.
It was already given. It is the only way to go.
Exactly. So yeah. So again, I mean, if you are looking at shapes, I might tell you here that if your distance metric changes, then your shapes will also change. Okay, so don't look at shapes, just look at the values. Values will never lie to you.
Thank you, sir.
Yeah. Okay, so
you may stop the recording somewhere. We would like to say goodbye to you.
Okay, I'll stop I'll stop sharing my screen also, maybe. Okay.
So your sessions are